Good afternoon, everyone. Welcome to another session of Network Seminar Series hosted by the Center for Network Intelligence at the Robert Bosch Center for Cyber-Physical Systems, IIC. Today's talk is by Professor Ayalvadi Ganesh, and he will be speaking on social learning in multi-agent, multi-armed bandits. Professor Ayalvadi Ganesh is an associate professor at the School of Mathematics, University of Bristol. His research interests include large deviations, queuing theory, random graph dynamics, and decentralized algorithms. He won the Informs Best Publication Award in 2005 and the ACM Sigmatrix Best Paper Prize in 2010. Before we move on to the talk, we would like to request the audience to subscribe to our Google group for information on future talks. You can also visit our website for more details. Finally, we request the online audience to keep your microphones on silent for the duration of the talk. And for questions, you may ask Professor Ganesh directly or type them in the chat box and we will moderate it quickly. For the in-person audience, we have arranged coffee at the coffee machine in the adjacent building. Please help yourself to continue conversations over coffee after the talk. Over to you, Professor Ganesh.
Thank you. Thanks for the introduction and for the invitation to speak here. Please feel free to interrupt at any time if you have questions. So today I'm going to be speaking about multi-armed bandit problems, but also with multiple agents and ways they can coordinate to learn about the problem. And this joint work with several people I'll mention in the context of specific papers who was involved in it. Okay, so an outline of the talk. I'll start with some informal motivation, and then I won't assume that you know about multi-armed bandits, and if you want me to go faster through those bits, please let me know. So I'll start with the single agent setting and just review some bounds and results for that setting, and then go on to precisely state the model of the problem for the multi-agent setting. Then I'll just describe the main results. We won't go into details of the proofs, but just some of the ideas behind them. And I've left the related work for the end so that the model is clear already and maybe it's easier to appreciate at that point. And then I'll finish with some of the problems. Okay, so here's a toy model to motivate it. You want to know what the best restaurant in Bangalore is. You can try them all. That will maybe take you a long time and it will and a large budget to do that. So maybe that's not feasible. But can you still learn this by maybe talking to other people? That's basically the motivating question. And for this particular example, to even post this, then implicitly when we are talking about the best restaurant, we are saying everybody has the same preferences. So we'll all share the same ranking. There's no diversity of taste. And not only do you share a ranking, you can somehow maybe associate a numerical score with this ranking and communicate this numerical score. That's kind of the implicit assumption here. But you don't, when you visit this restaurant, you don't perfectly sample this numerical score because there's some variability from day to day. So you get a random observation of the quality, whose mean is its true score, but there's some variability. That's kind of the thing. Yeah.
If my understanding is correct, so everybody has the same ranking.
Everybody has the same ranking. Everybody will assign the same numerical value.
Same numerical value also. But there is some randomness. What is the randomness there?
So the randomness is just the restaurant itself is variable from day to day. So you go today, its true value is 5. You measure 5.2. I go tomorrow and measure 4.8, etc.
So that means that there is a realization of ranking every day also, right? That today I might rate you differently than tomorrow, so my ranking will change, right?
Okay, yeah, but what we are interested in is the mean ranking.
Oh, just the mean ranking.
Just, yeah. So it's okay. So maybe we go, as I discussed the multi-armed bandit problem, the assumptions there will be implicit. So there's a true ranking, but there is some Okay, so so your question is the randomness because of diversity in the individuals? That's not how we are thinking of it. There is some intrinsic randomness to the measure. So even if two of us go on the same day for whatever reason, we wanted different dishes, we get some randomness in the measurement.
Okay, and so what I do is I go to a restaurant and I just give a score, and the score can be ordered, and that will be somehow be close to the true ranking, which you think is underlying.
Yeah. Okay, and some other applications, maybe this is more realistically the motivated application. So,
Sorry, one more thing I didn't understand. So if you go back in the so you said a single person cannot do it. So that means unless I visit the restaurant, I do not know what score I will get. Is that
that's right. That's
because there's so many restaurants that I do not know what my score would be.
Yeah.
But if I would go there, I would give the same score as anybody else. I mean,
yeah, after the
calculate
standard models, you would give the same score as
so you're trying to remove the control, right? Pritam, you are the Zoom ninja. You need to stop this and fix the removing that stop.
the related method of floating. There will be a height floating control there. Height floating maybe.
Height floating. But you also click something as that, which made it this fluid thing, right?
Yeah, how it's just make it float. Yeah, so another motivating example. So you have websites which display ads in response to search terms, and they are trying to optimize, say, click-through rates. And now, so you have these data set. So the ads are being served around the world from different centers, and each of them can measure locally in response to what it's displaying, what the click-through is. But you want to optimize overall. So do you want all your servers all over the world to communicate the click-through rates for every possible ad and every possible search term? This might be unrealistic. So again, how do you maybe optimize, learn these click-through rates with minimal communication?
So I didn't understand the relation between this and that, right? Here, are assuming that all ads also have an underlying ranking.
All ads have an underlying click-through rate for a given search term.
So then you would just want to display the ads with the highest click-through rate.
Exactly. If you knew that. But every individual who's clicking is random. So the click-through rate may be 0.1, but every individual either clicks or doesn't click. So
but this is just the random noise, right? The mean of the ranking is still you're gonna assume is universal and everybody agrees on that, right?
Yeah. So that's the kind of. So there is a true click-through rate which doesn't show geographical variation, and you want to measure it. Okay, and some other things like what's the best route to commute to work, or which brand of page you put to purchase, etc. So these could be other such motivation examples. And then there are two kinds of questions you can ask in these contexts. So one is how do a group of agents, a large number of agents, make optimal decisions? How should they make them? And you could also ask how do consumers choose which brand of fridge or car to purchase? And how should they do it if they were doing it right? So these are some more different questions. And how should you do it is the kind of thing that we are more interested in computer science or over departments. And what agents actually do is what social scientists and economists like
to discover what the best car is, right?
So for each individual, it's hard, right? Because you're only buying one car. And all you can say after the practice, I'm happy with it, or I'm
You're right, but see, as you said, every individual is stochastically similar, right? And our needs are sort of same, right?
Yeah.
So if historically it has been discovered what is the best car to be chosen, because that's the number one for everyone, then if you wait long enough, then everybody is discovered and they all buy the same car, right?
Yeah, that's true. That is under the assumptions of this model, there will only be one car which everybody will buy.
Right.
Yeah. Indeed.
Okay, this is okay. My understanding
Yeah,
is
under the assumptions of this model,
Right.
that's right. Okay, then you can of course say, yeah, this is maybe not the set. This is a very simple setting. You can say we should be studying contextual bandits, etc. You have a budget, you have certain preferences for price versus quality, trade-offs, and then you can make it more realistic in all those ways. But we start with the simplest.
No, I'm okay with it. I was just saying that my understanding is okay. That if you wait long enough, then we all buy this.
Then we all buy this. Exactly. That's what is going to happen for the problems we study. Yeah.
Is it team problem or is it team problem?
It is in effect a team problem, so we want to collectively optimize. Yeah, I'll write down a precise optimization problem later. Yeah, what you want to do is optimize the sum of the utilities, if you like, or minimize the sum of the regrets. That's how we post. Oh, good. So now we'll get a different problem. So let's now look at the multi-arm package problem with a single agent. So now we don't have multiple agents. So now we have just one agent, but there are k actions around to choose from. Time is discrete, and at each time step, the agent plays one arm and observes the reward for the arm played. They know nothing about target arms from that set. And we assume that you get random IID rewards when you play this arm. Okay, and these are mutually independent, reasonable assumptions. So you observe the reward on arm I only if you play that. And then you have to decide which arm to play. And now, okay, so
So the arms are not identical, right? IID is only the same arm you played every time, right?
that's right. So the rewards for a given arm are IID across time, and rewards from different arms are not identically distributed, but they are independent. And okay, so for each arm there will be its corresponding mean. I think I introduced that notation later. And you want to play the arm with the highest mean reward. That's the set. Okay, and
Clarification. You can go back and the agent I observes something that he has played. Or
there's one agent,
only one agent.
For now.
One agent.
but in future, agents will only observe the arms they have played. They won't observe what other agents.
Right now,
Right now, there's just one. Yeah, and your regret is the difference between not your actual reward, but your expected reward of the best arm and the expected reward of the arm actually played. Okay, so not the actual. And this you add up over time, and that's your regret after a given time. And the goal is to minimize your regret in the long run. And so you could just explore for a short amount of time, decide what's the best arm, and keep playing that forever. But then you might have made a wrong decision. So over a long time, you'll get a lot of regret. But if you keep playing different arms to become very certain what's the best, you may be spending too much time exploring, and then you don't have enough time to play that arm. And so there's a trade-off. And the question is how best to do this trade-off. Yeah, and we define regret with respect to expected reward, not sample path, which is your question earlier. And somehow this is not unreasonable because the sample path reward involves randomness that you can never learn. So the bit you can learn is the expected thing, and so that's what you try to optimize. Okay, and so we are going to only look at the simplest case here. Some of these results can be generated recognize, but we'll assume that the rewards are per. So you either get a 0 or 1 reward, you're happy with your restaurant or you're not happy. And so mu I is the probability you get the reward 1. Let's say we have wrapped arms, so arm 1 is the best, has the highest mean reward, and it's strictly bigger than arm 2, and then the rest are bigger.
Sir, there is a question from the online audience. What does the phrase randomness that cannot be learned? Can we not find its distribution?
Okay, we can find its distribution, but we cannot find for a given sample what its value is going to be. So we cannot optimize with respect to the sample path, because when you are playing an arm, you don't know what realization you're going to get because they are identical. So you can play the arm with the highest mean reward. So, okay, what will become clear later on is that your regret for the means is of order log t, but your sample path fluctuations alone will be square root of t. You cannot beat that square root of t fluctuation in the sample path. So if you say how well has the sample path of what I've played done compared to the best, you will always see a regret of square root of t. And somehow that's not what we want to look at. We want to look at what the expectation is. Yeah.
So fluctuations will be order of square root of t, log t, or square root of t.
If you look at the worst case over the all time, it's square root of t log t, but at a given time, it's square root of t. Okay, so that's yeah. So that's the notation. The mu i's are the mean rewards, and the regret is if your known arm 1 was the best and played it for all t times set, this is the reward. Expected reward you get minus the expected reward you actually got. That's your regret. And then there are 2 questions we can ask. Are there first is what's the best you can do, meaning are there fundamental lower bounds on what you can achieve? And then secondly, can you actually do the best that can be done? Are they efficient? So in some sense, the first is an information theoretic lower bound, and the second is a computational question. What's achieved? Can you computationally achieve what is information theoretically achieved? And the answer in this setting is yes. Okay, so this problem has a long history. It goes back even to the 1920s or 30s, where it was not actually stated formally, but it was solved before it was stated by Thomson, who was a medical doctor, and he wanted to know how to do clinical trials. So he was trying to assign patient to the best to alternative treatments. And we wanted to know how to make these decisions and came up with a method which is now called Thomson sampling, which turns out to be optimal. And he did this without being a trained mathematician or computer scientist or whatever. The formal statement and analysis of the problem happened in the 60s, starting with the most significant work was that of Fly and Robbins. They showed that for this problem, you cannot achieve regret better than a certain lower bound. And what's the lower bound? You sum up over all the arms, the gap between the mean reward of that arm and of the best arm. And the bigger the gap, every time you play it, you get a bigger regret. But this gets divided. So in the denominator, you have the Kullback like the divergence or the relative entropy between the best arm and the arm you are playing, UI. And this is a measure of how distinguishable these arms are. If μi is very close to μ1, you cannot tell them apart. So you might end up, you might see your sample for arm I might look better. So you might end up thinking this is better and play it more often. And so this is a measure of how difficult it is to decide between two marks. And then you get log t. So one takeaway message is that the regret after time t scales like log t, or the best you can hope for is a log t scaling, and the constant in front of it depends on the gaps between the numbers. And maybe this is one intuitive reason you might expect this log t scaling is that in the classical hypothesis testing problem, your error probability decays exponentially. So with about log t tests, you should be able to get an error probability of 1 over t. And so this is the kind of, and then you should be able to make the best decision from then on up to your time. So that's some reason to expect this. And again, the error probability in the hypothesis testing problem indeed depends on the KL divergence. So you might intuitively, you can see intuitively why that's turning out. Okay, and so the thing to remember is log t scaling. And okay, if all these gaps were identical, delta. Also, if the gap is small, then Pinskers inequality says that your KL divergence is approximate, is bounded in one direction. Yeah, it's bigger or equal, I think, to this thing. And in fact, if the gap is small, there's an approximate equality in this equality. And so your regret scales like log t, but it also scales linearly in the number of arms because you are summing over k arms of roughly the same quantity. So it's your regret grows linearly in the number of arms. So this is saying that if you have a single agent and k is huge, then you have, in some sense, a difficult problem. You have huge regret coming from a huge number of arms. And that motivates the multi-agent setting, and so with lots of agents can we do that. Okay, so just to so I gave this Lion Robbins lower bound of the regret, and there is in fact an algorithm which gets the logarithmic scaling right. This algorithm is called the UCP or upper confidence point algorithm. And the rough idea, I won't go into the details. You play the arm with the highest mean empirical mean reward you have observed up to that time. If the second term weren't there, that's what you would do. But the second term says, if an arm has not been played too much yet, then give more preference to that arm. So you balance the arm you think is best with some measure of your uncertainty of the arm. So arms with more uncertainty get boosted by this term. And this scaling is somehow optimal. And this is the UGP. And that achieves log t scaling, but not with the best constant. And this has been subsequently modified by a variant called KUCP for obvious reasons, and that has been shown to be asymptotic for single agents. And then there's also this Bayesian algorithm I mentioned, known as Thompson sampling, which also achieves this. And then so there are efficient algorithms which can achieve the theoretical best. Okay, so now let's move on to the multi-agent setting. So we have a large number of agent arms, and then we also now have a large number of agents. Otherwise, it's the same setting as before. They don't know very about parameters, but they can communicate with each other. And very loosely speaking, we don't want them to communicate too much. I won't make it too precise. And the objective is to maximize the aggregate long-term reward. This was the question. So it is a team problem in that sense, or to minimize that. Okay, so I'll skip this because we are running short of time. So there's a whole other literature on social learning looking at somewhat different problems. If you have questions later, I can chat about that. So sticking with our multi-arm bandit setting. So at each decision epoch, time is discrete again. An agent can play an arm or or it can communicate with one of its neighbors or both. This is kind of the model. And the communications shouldn't be very huge. That's loosely what we want. So, for example, you can recommend an arm and you can give some information about the arm, but you shouldn't say everything you know about all the arms for communication. Very useful. And again, we want to ask the same questions. What are the fundamental lower bounds and what can be achieved?
What is the constraint on the communication?
I'm going to keep it loose for now.
So, because you said you can do both, you can play an arm, communicate, or do both. So if I was not sure of the constraint, I will do both, right? Because you can always
you can do
benefit
Yeah,
by communicating. Right?
yeah, that's fine. You are allowed to do that. We will show that very little communication is enough to achieve asymptotic optimality. So we haven't made it to this. So we don't need okay, so let's first look at an upper bound on what's achievable. So, well, if there is no communication, if you don't allow any communication, the agents are to act independently. And so they will each achieve the regret of the single agent problem. So each agent can achieve this using KLUCD or whichever algorithm is optimal for the single agent problem. So this is the Lion-Robbins lower bound that's achievable. And then with no communication, you get n times that. Each of them achieves this regret, so you get n times that. So this is achievable with no communication. Now, if there is unlimited communication, then potentially it's like all the agents are effectively a single agent. And so what's the best you can do? In t time steps, there are nt plays of the arm. So you get the Lion-Robbins lower bound with just that change in them. So the n has gone from out there into the logarithm. And so this is the best you can do. So then,
Is it obvious that you're looking at a situation that there is no communication at all, but that could actually be independent randomness, like today's newspaper that everybody has access to, which would enable them to coordinate, but still the newspaper entity items are independent of this. With that common randomness, is there still this kind of a result, or is common randomness enabling?
good question. Okay. We haven't thought of that, but I don't think it can help. You can somehow say, yeah, you can say we will all play the same thing or we will all play different things by using the common randomness. But since you can't communicate, I'm not sure how you gain from it. Yeah, it's not clear to me how you gain. You could reduce the variance, but I don't see how you gain from it. Okay, we haven't actually thought of that. That's an interesting. Okay, so yeah, so then the question we want to ask is, so with no communication, you get almost 10 times the regret you get with full communication. Can we close this gap with allowing very limited? And so we have a series of cases where we successively close this gap, and that's what we're seeing. Okay, so the first result we had in 2019, so this was joint work with Sanjay Chakote and with Austin and Abhishek Sankarani, who was then a PhD student there, and now is a postdoc at Berkeley. Okay, so let's say G is the complete graph, so you can talk to anyone you like, but you speak with one person at a time, you can choose them as you like. Then for this setting, we presented an algorithm where we achieve a regret. So the coefficient of on log t is k plus n log n. Okay? Whereas if you looked at the form for the no communication setting, it was k times. So instead of k times n, we get k plus n roughly up to this log n. And if k and n are roughly of the same size, then it's almost as good as the full convolution set. So this is the coefficient of log t. This is how the regret fails over time. And so that this is in some sense close to optimal. Of course, there's also a constant factor. It takes a while to get to the scaling. So you are spend quite a bit of time learning things, and during that you get a big constant. So you do incur a regret, not just of k, but of you get multiplied by log squared n roughly, then you get some additional terms. So this is our regret bound. This was the first regret bound we achieved. So this is within polylog n.
And delta is much smaller than 1 by log t. Then
No, delta is constant. Delta is fixed, and we are looking at the t going to infinity set. So yeah, there is. So people are interested in gap independent bounds, but here our bounds depend on the gap. We don't know the gap, but our performance depends on the gap. The algorithm doesn't use knowledge of the gap.
So what was the algorithm? You said it, maybe I didn't catch it.
I'll say that I'll describe the algorithm later. You had questions?
No, I was, is it an upper bound or the middle? Right?
This is for our algorithm. Yeah. So this is, so we say we have an algorithm which achieves this upper bound.
So in what sense is it optimal? What is the optimal?
So the optimal was k log n t. And if n is roughly the same size as k, if n is proportional to k, for instance, so this is it's within a log n multiple of optimal. If n is k squared, then maybe it's not optimal.
No,
But-
what I'm trying to understand is more basic. The optimal, the notion of optimal regret, that is.
The optimal regret is where there is unlimited communication, and therefore they are behaving like a single agent.
But then shouldn't we have a lower bound? Because that's optimal regret should be that.
So for that setting, the Lion-Robbins lower bound is achievable because there are algorithms for the single agent setting. So I'm saying in the unlimited communication case, you can think of the multi-agent as a single agent, and therefore you can achieve the Lion-Robbins bound for the single agent setting. And that was this bound here, where so it's if all these are the same, you get the k term here over delta times log n.
One comment.
Yeah.
So when everybody has full communication, there is still this
Simultaneity.
yes.
Yeah, so we are ignoring the, so let's say asynchronous. Let's say they take
One
as a
at a
chance one.
so in the small delta regime, the decentralized bound is better. Is it? Bound on the because of 1 by delta squared.
The 1 by delta squared goes only in the constant. So it's not there in the log t. So this is a bad term. I'm not trying to hide that this is a bad term, but somehow we are ignoring this. We are saying we only want to know what happens in the long run. So we are going to ignore this huge constant, just focus on the coefficient of log t. And this coefficient is, if n is proportional to k, this coefficient is pretty close to the best you can achieve. It's only a log n factor worse than the best you can achieve.
So you're also assuming that the setting is decent, in the sense that I cannot decide a strategy before.
Yeah, or we are saying maybe there is a complicated method where you can decide a strategy.
For example, one agent can find out what is the best count, and then
Yeah.
communicate the best count to everyone. In that case, you don't incur regret for the other elements.
Yeah, but that agent can play on, so everybody plays once per time slot. So what are they going to do the
So
rest of?
it's not like agents have the choice to not play.
Yeah, They don't have choice.
You have to play.
Yeah, they have. But more importantly, the point I'm making is you might come up with a clever algorithm and say you can do better. That's fine. What we are saying is without doing all that cleverness, we are only slightly worse because you can't beat k log mt over delta. Because that's the lion calculus.
At most you can share the software model.
Yeah, exactly. And which we will do soon. So in this paper, we had this term, and then we improved on this result. And we shaved off that log n term. So on log t, we just have now the line problems kind of. It's a bit worse. We didn't get the KL term. We got 1 over delta I. So we got the same sort of behavior as UCB gets in the single agent case on the log t term. And in the constant terms, we have somewhat worse behavior. We have worse things. And we also in this setting considered general connected graphs rather than the complete graph and got some bounds depending on the graph. Okay, so it will become clear later on why it depends on the conductance, etc. It depends on some properties of this communication matrix over this graph. But the main thing again to take away from this is now on the log t, we have got rid of a log n term. So it's only k log t over delta. But
we didn't understand the communication matrix. Did you explain that?
okay, so we are saying so this matrix could either be part of the thing you're optimizing over, or it might be something imposed on you. So you have a graph. You can only talk to your neighbors on the graph. And our algorithm says that every time I talk, I'm going to randomly pick who I talk to according to this matrix.
PUV is the stochastic.
PUV is
And is the communication assumed to be instant or like?
yeah, it's instantaneous. We don't worry about communication delays. So you get, when I send you a message, you get it instantaneous or within that one time slot.
In the stopping problem where you're trying to find out the optimal which one is best. Even because, of course, the regret is there, it's not a notion of regret, it's expected time to stop. There, the constants are also known. So here, is it known what the best constant that multiplies the log t is?
For the regret, yes, it's known. That's the line drop.
So that's the mu1 minus mu1 by kl. You're not achieving that.
We are not achieving that. So we are getting the correct log t scaling without a log n term. We got rid of the extra log n term, but the dependence on k, that prefactor is not quite exact here. And then we further improve that. Yeah, okay. And here the other person, Rashi Chawla, is another PhD student at UT Austin. And then subsequent work with Bristol. Yeah.
Seems like this communication matrix doesn't affect your dominant term of log.
No,
It will be constant.
And that I'll explain why that happens. Yeah, and then we subsequently further improved this and got the optimal term. This probably should be long int. Okay, I should correct that. Yeah, so we get the optimal scaling in the long time. So the time scaling is optimal. Okay. And then there are again constant terms which could be quite far from optimal. Okay, so that was
Just one comment, because if you put log NP, that will be absorbed into the polylog n, because the log n will come out.
Yeah,
So
that's
I think that is probably what.
that's probably what. Yeah, that's, okay, So this was, so this was our last piece of work. So progressively we got the best possible constant on the log t with slight refinements. So I'll now describe this gossip insert element algorithm from the second paper. This is works, and then I'll mention. So what we do is at the start we agree on a partition of the arms. So I'm going to assign a subset of, we are going to cover the arms among the agents. So between the different agents, all the possible actions will be played. So I'll assign to each of you a subset of arms. And this we call it sticky set. But this will never change throughout the algorithm. But in addition, you will play a few extra arms, and here it's just 2 more. And these will be based on the communications you send and receive. And the form the communications are going to take is very simple. Here, I'm just going to periodically recommend them. That's all. So I'll illustrate with an example. So there are 10 arms and 4 agents. Okay, so I've assigned these 10 arms in a certain way initially to the 4 agents. So the box is the arms that each agent has. And so between them, they cover all the possible arms. And I also randomly assign these extra 2 arm sections. And this set you're not allowed to change. And the point of this is to say that you don't make, if you make mistakes early, you will never throw away the best arm by making an early mistake. Somebody will always keep the best arm in their set and keep exploring. So you can correct your mistakes later on. But these are changing.
And these are changing at each time. So the 6
The extra arms are changing. The extra arms are changing. Not at each time step, but occasionally they are.
So ideally, a time progresses in that extra arm, the correct one to settle in.
Exactly. That's right. So how do these things? How does the algorithm work? So we divide time into phases, and within a phase, each agent is, let's say, user. It's your favorite single agent algorithm over its set of arms, which is both its sticky set and this 2 extra arms. Okay, place UCB over all its arms. And at the end of the phase, it will just make one recommendation. It will recommend its most played arm to one randomly chosen algorithm. And it also receives recommendations because the choice is random. It may receive no recommendations, one recommendation, or many. If it receives many, it will just pick one recommendation at random. It will add that recommendation to its extra set, and it will throw away one element from its extra set, the least played arm from its extra set. And then these phases are going to grow longer. Slowly. Okay, so let's just say the same thing.
Sorry, one question. So, I mean, if this probability of communicating is low, right? That means even if I know a good, I'm not telling other people, right? So won't this affect your algorithm somehow slow it down?
It will slow it down. So you could speed it up by telling all your neighbors instead of one of your neighbors.
But this is now related to exactly a communication constraint, right? That this probability sort of decides how often would I communicate, which is the total amount of communication which will happen in that.
Yeah, I think one could change the constraints. You could formulate the model either way. So the point is, we have already achieved optimality for the time scaling. So you're indeed changing this like your constant.
Did not show up in your equation. So
It doesn't show up. And I'll explain why. It doesn't show up. Yeah.
No question. So you're asking each agent to throw away one from the non-constant set. But it might be that one of them, like for example, one might be the best.
Yeah, and it could end up going with them.
Do you want to throw away the worst one or no? It doesn't
You
matter.
throw away the one you think is worst, which may not really be the one.
It's possible that one, no?
It's
But
possible
you
that
are
one's
trying to not throw away randomly, but worst one.
Yeah.
So what is your expectation that eventually if you get this one again, you will keep playing it again and again somehow? What
Yeah,
is the expectation around
that's
it?
the idea. Yeah.
And why would that happen? Go because somebody giving you also its estimate of the
Yeah.
I see.
Yeah. One comes into everybody's set.
Eventually, right?
Eventually.
We end with high mean.
Yeah.
High mean is this.
You have the questions.
Yeah, I mean, why two instead of just picking one? Because you
So
want
this-
the best one to be in the non-sticking set.
That's right. I'm just saying this may be what happens as an instantiation of the algorithm. So I'm explaining how the algorithm works. So these are your sticky sets, and these are your non-sticky arms. You have played it for one phase, and within that one phase, just by chance, you observe two being the best arm. Just by chance. One is the best, but you don't know.
Size of the non-sticky set
Mhm.
can be one instead of two.
Yeah, it can. We did improve it later. For some reason, we thought we needed at least two, and it can be in fact just one. Yeah, it can be just one. Okay, so these are what you observed to be the best in one phase, and these arrows are saying who you are recommending to. Okay, I didn't put something to it. Yes. Okay, so this agent thinks arm 2 is the best, recommends it to this agent. This arm thinks arm 6 is the best, recommends it here, etc. This arm thinks arm 1 is the best and recommends it, and so on. Okay. So you receive some recommendations. So this agent receives one as a recommendation, but it already has one in it, so nothing changes for this agent. This agent receives 2 as a recommendation, so it will keep 2 and eject one of these other arms, whichever it thinks is first. Is the algorithm clear?
Is there a kind of a memory between the phases?
No, we don't assume memory.
There is a memory propagation, like in a Markov way, that you're getting the arm, which is recommended by the previous page and something.
Yeah, but the analysis gets, so we don't keep, so, okay, so in terms of your UCD parameters, you don't carry over your estimates from the previous
Or
page.
you don't carry the you had. So
It simplifies our analysis. If you carry it over, maybe things are faster. You can probably get tighter bounds.
So then I didn't understand. What do you do at the second phase? You restart with just keeping the cells,
These arms that you have.
the sticky and non-sticky set.
Yeah, so now after a phase has ended, you have changed some of your non-sticky arms. You restart the next phase as if you knew nothing about this.
Okay, so everybody's need you don't know.
Yeah.
But you know which phase you are in, because
You know which of the phase, you know the length of the phase, you know which phase you are.
Why is that important?
The lengths keep growing longer. The phases are going to, so the first phase will be of length 100, the second will be of.
No, for the algorithm, why is it important? I mean, I can see for obviously you want to keep track, but why this?
For the algorithm too, it's important.
But I don't understand why it's important.
At least for the way we do our proofs. If you don't make the phases longer, you probably have to carry forward information from one phase to the next. Otherwise, you won't get provable optimality. Okay, and these are the arms which were worst and which were rejected. Okay, and then we improved this to say the things that gave the optimal were to replace UCB with K and UCB, and then to indeed improve instead of having 2 extra arms, not just 1 extra arm, as you pointed out. And yeah, we only communicate once per phase, and the phases are growing longer, so you have sublinear communication, very little communication here, and that's enough. Again, and that already gives you optimality for the time scaling of the regret. With more communication, presumably you can do much better in the short term. But It gets very complicated to analyze, so we didn't do that. But certainly that could be an interesting problem.
So I thought that when you communicate not just RMI, we also get the estimate of the mean, right?
We don't, we just communicate that. That's all we do. Again, you could give that information, but then we have to analyze what you do with that information. And so the less you do with that information, the easier the analysis.
No, so the problem with that is then suppose you give me one, this is the best, but because I've never played it yet, right? I'll have to have enough
You have to
exploration for this one to become the best, right?
Yeah.
Otherwise, because I will always keep throwing it out because just I've not explored.
You could. And that's what makes the constant turn back. You could throw it away many times, but it's a large constant. And that's all. So the idea is indeed very simple for the analysis. And it relies basically on gossip spreading. Or even just gossip spreading in that, it quickly helps the constant term a bit. So the idea is you have n nodes, one of which, okay, so forget about the about this bandit problem. Let's just talk about gossip. And the gossip problem is the following. You have n nodes, one of which knows the rumor. It is discrete, and every time any node that knows the rumor pick someone at random, either within your graph or on the complete graph, and tells them the rumor. So if three of us know the rumor, we each pick a friend uniformly at or according to some metrics. Some of your friends, you prefer some of your friends to others. So this was first studied on the complete graph by Grimet and Cleese. And then they showed that the rumor spreads to everyone in log n times stocks. And Patel basically reduced the spread. So he showed that it concentrates even more sharply around log n. And Jansson studied the continuous time model and again got the log n scaling. And then if you do the same thing now, not on the complete graph, but on some other graph, you can get terms which depend on the conductance of this matrix. So that tells you how quickly the thing spreads. And that essentially is why this term appears in the constant. And if your graph is very nice, then essentially this thing is constant. It doesn't depend on the size of the graph. So you get some of it. Okay, and the idea of the proof is basically the following. Now, the faces keep getting longer. And so suppose you have the best arm within the active set. The chance of making a mistake in any phase and not identifying it correctly as the best arm keeps getting smaller. It's e to the minus something times the length of this. So it keeps getting smaller. And so because the faces are getting longer, then if you make them longer quick enough, then Borel-Cantelli says that you make only finite mistakes. You can make mistakes, but you only make some random finite number of mistakes. And so eventually, if you have the best arm, you will always recommend the best arm. And once you hear the recommendation for the best arm, you will never throw it. So it will always be there. And so eventually, you'll end up playing UCB over sets which contain the best. And that's basically that. That's it. And so for this random bit, which is long, consists of lots of phases, contributes to the large constant term in front, but it does not affect the boundary scale. That's the idea. Okay, I think we are quite short of time, so I'll skip the simulations, which are not that surprising, and then talk about related work. Kolla, Jagannathan, and Aditya Gopal, here they studied quite closely related one, but this was, I think, answering Rajesh's question from earlier. So their model was different in that you not only see the actions and rewards you get, but also your neighbors. You can't see everybody else, but you can observe the actions and rewards of your neighbors. So what they showed is that there are some algorithms which seem quite plausible, which seem reasonable, and are consistent for an individual person doing what's optimal for them, but they are suboptimal. If everybody does that, they are suboptimal. And so then they proposed an algorithm and showed that that is optimal. So here you can observe your neighbors. And then Martinez with no Kanate and Kawashimi looked at an algorithm where in each time step you communicate with all your neighbors. That was your question, not just with one of your neighbors. And so they also used essentially gossip-based ideas. So this was the same time, and we didn't. So we both kind of independently used gossiping ideas, but they used it to do a consensus or averaging algorithm, whereas we took. So there you would get your estimate values, your UCD parameters or something, and you would average them across your neighbors. Whereas we just took a recommendation of the norm and did cost on that basis. And then Anusha Ladika and Rhea Goldsmith looked at a Bayesian version problem. So there the agents use Thompson's algorithm. They have quite heavy communication. Maybe their algorithm also works with less communication, I don't know. But what they do is they maintain posteriors for all the arms, and they communicate at each time step. You communicate your parameters for all the arms. So you will only create one arm, an updated one arm, but you communicate everything and you average everything else. So that was the modern day. Okay, so these are all quite similar. They are all these are solving essentially the same problem. Then Vamshi, Abhishek, and Sanjay looked at a contextual bandit version. So this is not a simple multi-arm bandit, but there's some side information. So there might be the types of the restaurant, and then your reward depends on the quality and your taste preference across the types of restaurants. And then so far we have assumed everybody truthfully reveals their preferences, but what happens if there are malicious agents who give bad recommendations deliberately? If there are very few of them, can you somehow blacklist them and make correct decisions? And yeah, they have some mixed results.
What is the indication for 1 by delta square term? Like, why is it not 1 by delta?
1 upon delta square in the denominator is the difficulty of distinguishing the two arms. But then when you make the mistake, you only get delta regret. And so those two should cancel and get 1 over delta. But maybe some of the bounds have delta squared, I'm not sure. But the best achievable has 1 over delta. So this was some earlier bounds, is it? Or
In the second part of your boundary, delta square.
yeah, the constant. Yeah, I'm not sure. Why? Maybe that could be improved. It could have been just sloppiness. Okay, so that was related work, and I was finished with open problems. Yes, I think. Okay, while we have got the best constant in front of the log T, we have been very sloppy with the analysis, both the algorithms and the analysis of constant terms to simplify things, have independence across spaces, etc. If you can keep track of information from one phase, carry it over to the next phase, obviously that will improve things, makes the analysis harder. So maybe there's things to improve there. So something we are working on now is we are looking at the infinite arms version of this problem. So the arms you can think of as living on a metric space, the reward is continuous, Lipschitz continuous function of where you are on the space. compact sort of message for setting can be two similar things in the setting. That's what we're trying to yeah, okay. So we haven't looked at Western identification, that's also an interesting question. And everything is stochastic bandits version. There's a whole other literature with different methods of representing bandits, and we haven't done. There is some work on this now, I think, by other people, but I don't know much about that. Okay.
Do you think the phase lengths would converge somehow? Or
Not if we want to use forever, because then you'll have the same error probability. You'll have bounded error probability, so you'll make an. You want error probabilities to decay to zero fast enough to take some.
Any other questions? Thank you, Professor Ganesh, for an interesting talk. Once again, we would like to remind the audience to subscribe to our YouTube group for information on future talks. You can also visit our website for more details. Thank you and have a good day.